Alright, so we're done with source free RC. We're going to look at its younger brother, sort of. The source free RL circuit. Alright, R is resistor, this impedes current, symbol R, unit ohms. Now L is a bit different. L is an inductor. Okay, its symbol looks something like is a coil of wire with a conducting core. Alright, symbol is L and its unit is H for henries. H for henries. Okay. So what happens? You can look at it in the same way. In the same way a capacitor stores voltage. Alright. So we have our capacitor. Alright. Positive and negative voltage is being stored on both sides. Alright. And our inductor, it becomes a sort of magnetic field. Alright. So the purpose of this magnetic field is to prevent current from changing instantaneously. Right? So it charges up. It's a charge up to. The capacitor will have an initial voltage V0. The inductor will have an initial current. Let me write that. The initial current I0. So they both charge up, and once current stops flowing through them, once they stop being charged, they now become sources. So they will let out currents. They will let charge flow through them as if they were a source. The graph over time will look the same thing as a capacitor does, because they're both the same storage elements. They're both the same type of storage elements. So this should now be a maximum voltage. The maximum voltage I0 over time T 0, and eventually gets to 10 to 0. So I hope you're able to understand what happens in a source free circuit. At T less than 0, you have the presence of a source. That source charges your storage element to either V0 for a capacitor or I0 for an inductor. It's a charge it up. And once that source is disconnected at T equals 0, you get your maximum voltage. V0 for capacitors, I0 for inductors. And these become sort of pseudo sources, like fake sources. And they let current flow in the circuit, until they get completely discharged. And a value gets to 0. So let's see if we can do the derivation for the source free RL circuit. Okay. You have your inductor and you have your resistor as, that's not a pretty inductor. Oh my. Alright, that's fine. I'll explain that at the end. Okay. You have your ground. Alright, so what happens now is that you have current flowing. Alright. Current flowing through your circuits. Plus. Minus plus. So plus minus is our inductor value L, resistor of R. Okay. VL is the voltage across the inductor. VR, voltage across the resistor. Okay. So this is our source free RL circuit at T greater than 0. We remove the source, and now we have a simple smooth circuit. We're going to use KVL to analyze this one, the analog of KCL. So what does KVL mean? In a mesh, in a loop, in an electrical loop, the way we have a loop here, right? The way we have a loop here. The sum of the voltages, our direct sum of the voltages is always going to equal 0. So you don't have startup voltage, you don't have missing voltage. It's always going to equal to 0. So we're going to do the same thing. Since we're coming this way, this is going to be positive VR. So plus VR. Okay, I don't have to write plus. So VR. Take very good care of your polarities when you're deriving for KCL. So for KVL, you've got to be very careful with your polarities for your voltage. For KCL, you've got to be very careful with your current direction. So VR. So we go around and we come out and meet the positive polarity for the inductor. Plus VL is going to be equal to 0. Alright? Remember from Ohm's law, V is IR. Okay, so we have IR plus VL as L di dt is going to be equal to 0. I'm going to take this to the other side. So L di dt is going to equal minus IR. Okay, we're going to make the same substitution we did before to try and get I on the same side as the I. So that's 1 over I di is going to equal minus R over L dt. Alright, cool. We've got our simple differential equation. We can solve this from here. So if we integrate both sides, this is going to give us ln I is going to equal minus RT over L plus, I don't want to use C, plus V. Okay, cool. Let me use something more standard. Plus K, actually. Oh, what do I use? Plus K. Alright, let K be our constant for today. Remember to isolate I, we're going to raise both sides to the power of 2. Make both sides exponents of e. So e to the ln I is going to be just I, and there's going to be e to the minus RT over L plus K. Okay, this is together. Remember from our indices, we can bring this out. So e to the minus RT over L times, let's make e to the k equals b, alright, times b is this. So our I as a function of time, we're going to be b e to the minus RT over L amps. Okay, I of t is b to the minus RT over L amps. We can't leave it as this. Remember, I've got to solve for a constant b. So what does that leave us? Leave us with, remember, we set t equals 0. So let's look at it. When t equals 0, remember our inductor got charged up. So once it is charged up at t equals 0, we have a maximum current. So that's going to be I naught is equal to d times e to the R times 0 over L. This reduces to 0, and e to the 0 reduces to 1. Okay, so I naught becomes b, and we can throw this back into our major equation and end up with our final expression for I of t. So I of t is I naught e to the minus RT over L amps. Okay, e to the minus RT over L amps. So I'm going to make a very crucial distinction here that I didn't do when I was doing the RC circuits. In ROC, when you're dealing with ROC circuits, we have a very crucial parameter we call the time constant. Let me make a line. We should call the time constant. Alright, time constant, we denote it by tau. Greek letters small, is that small? Small letter tau. Alright, so what is this time constant? It's different for RL and for RC, but it is the time it takes for the parameter, okay? Because for RL it's to be current, for RC to be voltage. So it's the time it takes for the parameter to reduce by about 33%, I believe. Yeah, 36.7%. So it's the time it takes for the value to decrease by 1 over e%. That's about 36.8. So for RL circuits, what is our time constant? For RL circuits, your time constant is L over R. For RC circuits, the time constant is RC. Okay, I'll explain more on this on the next slide.